going to give you a 5-minute, well, knowing me, it's probably more like 10-minute lesson on finance between this screencast and the one that will come next week on expected values. You will have in 20 minutes time the nuts and bolts of a whole finance course. Anyway, I wanted to talk about the time value of money, which is related to the discounting that the chapter 5 opens with. And chapter 5 is interested in examining the trade-offs that people face as they consider investing time and effort into their own education, which is costly to do, as people weigh those investments against future rewards in the form of higher income or greater satisfaction or both. The assessment of costs and benefits that take place in different time periods is at the heart of what's going on there. So you need to understand a little bit about how economists think about evaluating payments, outgoing payments, and income that occur at different time periods. So let's get started here. Just some basic notation. We're going to describe the basic idea that $1 today is worth more than $1 tomorrow. That's the time value of money in a nutshell. And let's introduce some notation. We'll call the present value. That's $1 today. Or if we're going to convert future values into terms of today dollars. That's going to be the point of this analysis. So future value is going to be $1 tomorrow. Implicitly, I've got FV1 and when I say tomorrow, it means next period. It could be next year if we're analyzing things year to year. It could be next month, next week, or we could be doing daily compounding of interest. And that brings me to interest. We're going to call it R is the interest rate and we're going to just assume no inflation so that R is a real interest rate. So it's a real increase in purchasing power. And basically, if you invest $1 today, tomorrow, or next year, you're going to have your principal back. That's the dollar invested plus the interest earned. That's R. And in general, the present value, if we invest that, we're going to earn interest 1 plus R. If R were 3%, we'd have in the future, we'd have in 1 year's time, we'd have that present value times 1, that gets us our present value back, plus the interest rate. If it's 0.03, the interest earnings would be 0.03 times whatever that initial principal was. If it's $1, we're going to get 3 cents back. And that relationship holds in general, but in general, we know future values, or we're estimating future values, and we want to put everything in terms of today's value. And that's very easily done by some simple algebra. Present value is equal to that future value 1 period away divided by 1 plus, this by the way, a parentheses, it didn't really come out that well, parentheses, 1 plus R and parentheses. So this is the key relationship. It's hopefully pretty easy to understand in a 1 period model. And then let's extend that to 2 periods and then T periods. If we had invested $1 for 2 periods, we'd have that present value. And then the first year it would earn 1 plus R. That's how much we'd have after the first year. And then this whole sum of money is going to earn, we're going to keep it invested, it's going to earn another 1 plus R times this whole sum of money. That's the interest earnings. That's second year. That's going to equal whatever future value we'd have after we invested it for 2 years. And we'll call that FV2. It's going to be 2 periods away. Well, PV, and let's call period now is period naught. It's going to be equal to the future value in 2 periods divided by 1 plus r squared. Now, and then in general, same logic, we could write it all out, but in general, the present value of a payment or a receipt of income in the future is going to be whatever that future value is in time t divided by 1 plus r to the t. You guessed it. So that's the general conversion of a dollar, whether it's a payment, that would be a negative, dollar going out, or a benefit, dollar coming in. T periods away, that's the general relationship. And now, the text talks about net present value. And net present value, that net assumes, okay, we're netting something out, we're adding something and subtracting something. And indeed, that's right. Net present value simply connotes that we've had a stream of benefits. Let's say we have benefits coming in year 1, and we want to think about what those would be worth today. We'd have to discount that by 1 plus r because it's coming in 1 year. Let's say we have benefits coming in year 1, year 2, year 3. We discount those benefits appropriately, so we get them all into the same units, present dollar terms, present values. And let's say we had some costs that we're going to subtract off. Let's say we have some costs this year. Notice that we don't discount this year. We could say 1 plus r to the 0, but anything to the 0 is just 1. So we don't have to discount today's costs because they're already in today dollar terms. Let's say we had costs in year 1 and in year 2. If you had real numbers, this is really easy to do in a spreadsheet. This kind of thing is why spreadsheets were invented. And there we have it. And that's what's going on. Now, the book does one more thing that perhaps you followed and perhaps you didn't. What the book does is use, because you notice this is a lot of terms, and as if we had more than 3 periods, it would be even more terms. So the book used some mathematical notation to express this idea a little more compactly and also in the general case. So the net present value, the value at period naught of a stream of benefits and costs that took place over T periods, capital T is the length of time the benefits and costs are coming in. We're going to sum from today, T equals 0, to period T. We're going to sum the benefits and costs that come in each period, and we're going to discount those benefits and costs appropriately. Oops. And the appropriate discount rate for both benefits and costs would be 1 plus r to the t. And that's the net present value formula. And this is like half a semester of a finance course understanding that in detail. I'm exaggerating the simplicity of it all, but not by a whole lot. If you have this idea in hand, you can derive pretty much any of the formulas you use in a finance course. Up until you start looking at uncertainty, and then I'll get you there with the expected value discussion next week. The text goes one step further, and so we're going to talk about the Bhattacharya text, equation 5.1, that looks slightly different from the one I just had down. They make 2 simplifications. One's just notation. First of all, they follow this convention where delta, the Greek small letter d, Greek small delta, is going to stand in for 1 plus r. And that's going to be called the discount factor. 1 over 1 plus r, delta, either one is going to be the discount factor. They're the same. That's an identity. And then they make another simplification that's just by an assumption. They assume only income. You notice they just have I in period t, income in period t, not benefit in period t minus cost in period t. But that's really all they had to do then was call that present value rather than net present value. The net implies in finance theory that we're netting out costs. And then after they make those assumptions, we get the following. We just substitute appropriately, and we get they assume cost CT is 0, and then instead of B in period t, they call it I in period t. So then you get t equals 0 to big period t. That's the period over which we're summing. Instead of 1 over 1 plus r, the quantity to the t, they use delta to the t. It's the same. It's just expressed differently. And they use I, the income in period t, parentheses t. That's just an alternative notation to using the subscript. So there we have it. That's 5.1. This is where it comes from. Just a quick word on interpreting some of this stuff. Oh, I have an extra blank screen. Here we are. I use the ant and the grasshopper. I used this in my health econ course in the spring, and the students had never heard the ant and the grasshopper fable, and hopefully you have. If you haven't, I'll post it on Moodle. Let me know. Maybe I will either way. Anyway, the ant is this hardworking person who thinks ahead and values the future very heavily against the present. The grasshopper is just singing his songs, dancing in the sun, making fun of the ant, working all the time. Don't you know it's sunny out and you can just eat the grass? It's lovely. You don't have to work. You're just wasting your time. Well, the winter comes, and of course the ant has a bunch of food in their house, and the grasshopper can't eat the grass anymore, hasn't saved up, wasn't thinking about the future, and is dying in the cold. And this being an Aesop fable, the ant just says, "Go away," and the grasshopper goes off and dies. Fairly harsh reality in these fables. Anyway, delta has a nice interpretation as the ratio of $1 one period from now to $1 today. So if your discount factor is, say, 0.95, that means you weigh the future fairly strongly against $1 today. Yeah, it's worth less than $1, but 95 cents is pretty close. On the other hand, if someone had a discount factor of 0.65, well, 65 cents next year is going to be the same as having $1 today. That's a very, very steep discount rate. And I mentioned before, my son has ADHD. He seems to operate at a discount factor of, we call R the discount rate, delta the discount factor. I know the terminology is confusing. If we had a delta of 0.3, $1 today is worth 30 cents tomorrow. It's just like nothing compared to the dollar. And that inability to think through the future consequences of what you do today can be a real disability. We'll leave it at that. We'll work with this some in class, so come in firing on that.